Today's math question is, where did we get the quadratic formula from? We all have used the quadratic formula to solve quadratic equations. It's a formula we all remember, but where exactly did it derive from? That's what I'd like to illustrate today. So I'd like to start with the following. I want to square a binomial. So I want to square x plus k. And before I write the answer to x plus k squared, I would like to declare what the answer is not. And so the answer is not x squared plus k squared. The easiest way to show why it's not is, say I had 4 plus 3 squared. 4 plus 3 squared we know is 49. It's 7 squared. It's not 25. It's not 4 squared plus 3 squared. It's not 16 plus 9, 25. It's 49. So how do we square x plus k? The easiest way to understand how to look at it is we know when we square something, we multiply something by itself. So x plus k squared is x plus k times x plus k. And now the type of multiplication that I was going to go here, it's been called different things, and you can call it what you want, but what you end up doing is just multiplying everything here by everything there. So what I do is I have to multiply x times x. That's x squared, x times k, that's kx, k times x, that's kx, k times k, that's k squared. You notice I have the two like terms in the middle, kx and kx. They can be added together to become 2kx. And so I get x squared plus 2kx plus k squared. Now you may say, which is a very legitimate question, what in the world does that have to do with the quadratic formula? Well, let me show you. But before I show you, I want to point out a couple of things about the relationship between some of the terms in this answer and also the relationship between this answer and what we started with. So what we just found is that x plus k squared is x squared plus 2kx plus k squared. And by the way, I did x plus k. Had I did x minus k, it just would have been x squared minus 2kx plus k squared. The k squared would still be positive because minus k times minus k is positive k squared. All right. So I want to analyze a couple of things. First, I would like to analyze the relationship between the coefficient of x and the constant in this expression. Now, you have to understand, this expression on the right is a perfect square. It came from squaring something. Like if I squared 7, the answer is 49. 49 is a perfect square. So x squared plus 2kx plus k squared is a perfect square. It's a quadratic trinomial perfect square. A very big word for a very beautiful thing in mathematics, but this guy is a perfect square. And so when I have a quadratic trinomial perfect square, I want to recognize the relationship between the coefficient of x, which is a lot of times called b, and the constant, which is a lot of times called c. And if you notice, the coefficient of x is 2k and c is k squared. And what I have to do to the coefficient of x to get c is take half of it and square it. You notice if I take half of 2k, I get k, and then square it, I get k squared. So the relationship between the coefficient of x and the constant in a quadratic trinomial perfect square is that the coefficient of x, if I take half of it and square it, I get the constant. That's going to be important. Also, we want to understand the expanded form here on the right and what we call the factor form here on the left. So these are two equivalent expressions This one has just been expanded out by multiplication. Again, just like 3 plus 4 squared and 49 are identical, these guys are identical. So they represent the same thing. And so if I ever needed to take the expression in expanded form and put it back in factor form, I want to look how that works. So notice I have an x squared here, and then the factor form is just an x. Notice I have a plus, and this could be a plus or a minus sign here, and whatever it is, it'll be a plus or a minus sign there. But notice this number right here. This number in here is k, and k is simply half of the coefficient of x. The number that goes in here is simply half of the coefficient of x. To me, that's the easiest way of thinking of it. You can also think of it as the square root of the last number. Either of those two ways. So, here's the deal. So if we had a quadratic trinomial perfect square, so here's a quadratic trinomial perfect square. How do I know it is? Because if I take half of the coefficient of x, if I take half of 14 and square it, I get 49. So that verifies that's a quadratic trinomial perfect square. And if I ever wanted to factor it, the factoring is quite easy. X plus, and I'll take half of 14 and get 7. It's that simple. Another example, x squared minus 46x plus 529. Again, this is also a quadratic trinomial perfect square. How do I know? If I take half of the coefficient of x, half of 46 is negative 23, and square it, negative 23 squared is 529. So it's a quadratic trinomial perfect square. And so if I want to factor it, again, x squared goes to x minus, and I take half of 46, 23. Alright, so that's how we factor quadratic trinomial perfect squares. That's pretty important. And also, again, the relationship between these two numbers, that this number is half of this number squared, that this number is half of this number squared, is critically important as well. Okay. So we're going to put those two understandings together, and we're going to use a method to solve quadratic equations, which is called completing the square. And it's actually the activity from completing the square that's going to give us the quadratic formula. So I'm going to do a couple of examples of completing the square, and then I'll use completing the square to find the quadratic formula. So here is a quadratic equation. I'll do something very basic, not trying to change the world. These will be pretty simplistic problems. Okay, so say this is a quadratic formula, and of course a quadratic formula, say this is a quadratic equation, and of course there's various ways to solve quadratic equations. Here I'm going to solve by completing the square. You may look at this and see you can solve it by factoring or by some other method. It's true, but I'm trying to show the steps with completing the square. So to solve with completing the square, what we like to do is move whatever constants we have to the right side of the equal sign. And then we want to turn what's on the left-hand side into a quadratic trinomial perfect square. So if you recall, I need a number here, and I need a number here that completes the square. I need a number that makes this a perfect square. And again, remember the relationship between this number, which is going to be a constant, and the coefficient of x, is that it's half of the coefficient of x squared. So to find that number, I just need to take half of this number and square it. So half of 10 is 5, 5 squared is 25. And so I add 25. But of course you may also notice, once I added 25, I've changed the value of this side of the equation, so to make it equal, then I'll also add 25 to this side as well. And what that allows me to do, once I've made this a quadratic trinomial perfect square, I can factor it in a method we've talked about before. That's x plus 5 squared. Again, the 5 comes from half of the coefficient of x. I can add these two numbers, negative 25, negative 24 and 25 is 1. And you get this very easy equation once you complete the square, where all you have to do is take the square root of both sides. and easily solve from there. So I'll solve this one. So if I take the square root, this will be x plus 5. And the square root of this guy would be plus or minus 1. And so x will be negative 5 plus or minus 1. And negative 5 plus 1 is negative 4. Negative 5 minus 1 is negative 6. So the answer by completing the square will be negative 4 and negative 6. I want to do one more example of this. And then I'll show you how this is used to find a quadratic formula. So on my next example, let's say it's 5x squared minus 2x minus 3 equals 0. So I'm also going to solve this equation by completing the square. Now what makes it a little different from its predecessor is there's a coefficient in front of x squared. It's no big deal. Whatever they put in front of x squared I can get rid of by division. So the first thing I'll do is simply divide everything by 5. And we'll get x squared minus 2 over 5x minus 3 over 5. And now it's a problem just like the previous example. Sure, I may have some fractions, numbers are numbers. It doesn't change anything in my mind, so I'm going to repeat the same steps. So I'm going to move the constant to the other side. And next I'm going to find a number which completes the square. I'm going to take half of the coefficient of x and square it. Half of 2/5 is 1/5. 1/5 squared is 1 over 25. So I'm going to add 1 over 25 to both sides. Okay, so now I can factor the left. So this can be factored. Again, to factor this is simply x minus, you take half of this number, that's 1/5 squared. Now on the right, you have 3/5 times 1 over 25. You need a common denominator, that would be 25. So you multiply 3/5 by 5 over 5, that would be 15 over 5. That's 15 over 25 plus 1 over 25. So that would be 16 over 25. So you have x minus 1/5 squared x minus 1/5 squared equals 16 over 25. Take the square root. And the same thing will happen before. I'm going to go a little bit quicker because it's the same end of the story. This will be x minus 1/5 plus or minus 4/5. And then you add 1/5 to the other side. That's 1/5 plus or minus 4/5. And 1/5 plus 4/5 is 5/5, which is 1. And 1/5 minus 4/5 is negative 3/5. So there's my answer. And this completing the square method will work with any type of roots. So far in my two examples, the roots were rational, but they could be irrational or complex. This method still works. Okay, so here I was doing a certain method to solve a quadratic equation with numbers plugged in. And so that method worked, gave me answers for certain particular numbers that were plugged in. If I write just a general quadratic equation with no numbers really specified, if I write this as my quadratic equation, ax squared plus bx plus c, and set that equal to solve, when I solve this guy, I will get a solution which will always give me an answer when I just plug in the values of a, b, and c. And that's where the quadratic formula comes from. So we're going to do the steps of completing a square. Now again, like the previous example, there's a number in front of x squared. I'm going to get rid of it. I'm going to divide everything by a. So I divide everything by a. I have x squared plus b over a x plus c over a. And so next thing I'll do, this is a constant. This is the only thing that doesn't have an x in it, so I'm going to move this to the other side. And I'll have x squared plus b over a equals negative c over a. Next, I'll find the number that completes the square. It's the coefficient. It's half the coefficient of x squared. The coefficient of x is b over a. Half of b over a is b over 2a. And b over 2a squared is b squared over 4a squared. So the number that completes the square for this case, and again, I'm taking half of b over a. If you want to take half of a fraction, double its denominator. Half of 1/5 is 1/10. Half of 1 over 8 is 1 over 16. So if you want to take half of a fraction, just double its denominator. So half of b over a is b over 2a, and b over 2a squared is b squared over 4a squared. So b squared over 4a squared. And again, I need to add that to both sides of the equal sign. And so here, I'm going to put it in front of this minus c over a, because the minus c over a has a minus sign in front of it. And it'll be more aesthetically pleasing if the minus sign was behind it versus in front of it. So I'm going to write the b squared minus b squared over 4a squared, and then minus c over a. And now we're to the point where we need to factor the guy on the left. So again, this is a quadratic trinomial perfect square, because half of this squared is this guy. And so to factor it, I take x, there's x, I take plus, there's plus. The number that goes here is half of the coefficient of x. The coefficient of x is b over a. Half of b over a is b over 2a. So plus b over 2a squared. Now, these guys need a common denominator. And so the common denominator would be 4a squared. So you would have to multiply c over a top and bottom by 4a. So this needs to be multiplied by 4a over 4a. And so what will happen, this is b squared over 4a squared minus, so c times 4a is 4ac, and of course a times 4a is 4a squared. So to bring it together with one denominator, if you like, so I'm not particularly doing anything on the left. So x plus b over 2a squared. And here would be b squared minus 4ac over 4a squared. So I'm just combining them. They have common denominators. Now I'll take the square root of both sides. So the square root of this would just be x plus b over 2a. And the square root of this would be plus or minus. Now the numerator is not necessarily going to be a perfect square, so I'm going to leave it in the radical. So plus or minus the square root of b squared minus 4ac. The denominator is a perfect square, and so the square root of 4a squared is 2a. So I'm going to go ahead and take that square root. So divided by 2a. And then lastly, I'm going to move this b over 2a to the other side. Its sign is going to change, so it'll become negative b over 2a. And notice these guys have a common denominator, so I can write them as one fraction with one denominator. So when I move this over, I'll get that x, this will be negative b plus or minus the square root of b squared minus 4ac. And both these have denominators of 2a. So there you have how we get the quadratic formula.